Okay, so in the last puzzle, we used one word, or kind of not only then, but sort of kept alluding to the word on average, or how many do you expect to see. So in this lecture, we will use what we learned about probabilities and about combinatorics to talk about what it means to have something happen on average and how we can calculate that. So for example, you may have a program that solves some numerical task, and maybe you manage to figure out how long the program takes in the worst case, and it's some pretty large number, but you may want to say, but wait a moment, this worst case is hardly ever happens, and on average my program works pretty well. When you're doing your data structures and algorithm course, you will see a sorting algorithm called quicksort that runs pretty fast on average, even though its worst case running time is worse than the faster algorithm merge sort. So how do we talk about things happening on average? So the expected, imagine that there is a function that assigns to every outcome of an experiment a number, or so this function is called random variable, which is a complete misnomer because it's a function, it's not a variable. But for simplicity, you could think about outcomes of the experiment to be numbers. So for example, maybe an experiment is that somebody throws a ball, and an outcome is how far they've thrown that ball in meters. And say it's rounded up so that everything's finite. So the person throws the ball a few times. What is the average distance that this person hits? And you can imagine that the person probably throws the ball very far or not too far, not as often as they throw the ball somewhere in the middle of the range. So the probabilities of throwing the ball certain distance are different for different distances. Now, here's where the formula for the expected value or mean of a random variable comes from. An expected value is the sum of those numerical values associated with outcomes, where every one of those values is multiplied by a probability of that value. For example, suppose somebody throws a ball 1 meter away 90% of the time, and 5 meters away 10% of the time. Well, you'd expect the average to be closer to 1 meter than to whatever 5 meters. And this formula lets you exactly to calculate that value. So you say it's 1 meter times 0.9 plus 5 meters times 0.1, and that's my expected value. So again, a random variable is a function, in spite of being called a variable, from outcomes to numbers. It maps outcomes to numbers, like outcomes may already be numbers or maybe something else. And in computer science, most often you see random variables that count something. For example, you run the program and you want to know on average how many steps it takes. And that number of steps it takes will be your random variable that maps runs of the program to the number of steps a particular run took. And another very common random variable you're going to see is so-called indicator random variable. And that's a random variable that only takes value 0 or 1, or for no or yes. And it takes value 0 if the event did not occur, and it takes a value 1 if that event or outcome did occur. And now the expectation of the random variable, that's exactly the same formula that we just had, except we replace the a sub k, which we thought of as outcome, the distance somebody throws the ball, by the x of I, that random value function that maps our outcomes to numbers. And probability of the outcome that stays the same. And usually you see people writing the capital E to mean the expectation. So let's do an example. Suppose we roll two fair dice. What is the expected sum of their values? So think about it for a second. Do you expect would you be more surprised to see the dice coming up 1-1 than coming up with something that sums up to, say, 6? You may say, well, yeah, it's kind of obvious. There is only one way to get 1-1, and there are lots of different ways to get 6. So, of course, chances of seeing something with 6 are higher, so I can expect to see 6 more. But this is true, but there is this additional part here, is that you may see something a little bit less than 6, you can see something a little bit more than 6, and on average, you get something in the middle. So let's actually calculate it rather than saying 6 or not 6, because as you will see what the answer will be, and that's not going to be 6, because we are throwing two dice. So what values can our random variable take? Those are values between 2 and 12. 2 is when both dice came up 1, and 12 when they both came up 6. And let's calculate the probability of every one of those values, every one of the possible sums of the values of the dice. So probability of 2, probability of 12 is 1/36. There are 36 possible outcomes, and here we assume all of them are equally likely. It's fair dice. Probability of 3, same probability 11, is a little bit higher because you could get 1 and 2, or you could get 2 and 1, and both of them would give you 6. So it's 2/36. Probability of 4 is 3/36. You could get 1/3, or you could get 2/2, or you could get 3/1. Probability of 5 is 4/36, so it's 1/9. Probability of 6 is 5/36, and probability of 7 is 6/36, is 1/6. So you may be saying, wait a moment, why probability of 7 is more than probability of 6? Isn't 6 like the half? But remember, we are throwing two dice, so our minimum doesn't start at 0, starts at 2. So this is kind of the intuition why we get 7. So now let's calculate the expected value. And here we just multiply the number by its probability. We multiply 2 by 1/36, 3 by 2/36, and so on and so forth. And once you do the calculation, you come up with the number 7. And by the way, here we managed to get an actual natural number, but it doesn't have to be the case. You know all of those statements that on average people have 2.1 children. How can they have a 0.1 child? Well, this comes up from this calculation. So let's do another example, and let's do an example of a lottery. So there is a lottery here, Lotto 649, and it works like this. A player chooses 6 numbers from 1 to 49 in order, and during a draw they reveal 6 of the randomly generated numbers, and if the player correctly chose all 6 numbers, the first number, second, third, fourth, fifth, sixth, then they get the jackpot. And the ticket to this lottery costs about $3. Chances of winning the jackpot are roughly 1/14 million. So what is the expected amount a player would win if the jackpot is 5 million. So now we are talking again about expectation. On average, for an average person who plays the lottery, what would be the win? Well, you know what, if chances of winning are 1 in 14 million, then the average person is going to lose, right? So let's do the actual calculation. So probability of loss is 14 million minus 1 over 14 million. Probability of a win is 1 over 14 million. So what is the random variable that we are using? That the random variable that encodes the amount that the player shouldn't really say win, that the average player ends up with after playing this lottery. Can be negative, will be negative. So for all except for the winner, after playing the lottery, they are minus $3. For the lucky one, is the jackpot amount minus the $3. So on average, in expectation, if you plug in the number, an average player is going to lose $2.64 from playing the lottery. You may say, but wait a moment, usually it's not jackpot, there are other prizes and so on and so forth. You know, if you're interested, look up what prizes there are, look up the probabilities, plug them in, and see for yourself, on average, how much money an average player would win or lose after playing. So let's turn this question around a little bit, because the jackpot amount doesn't stay the same, and sometimes you hear it announced that the jackpot is getting bigger and bigger and bigger, and you may be wondering how big should be jackpot for you to really bother playing the game. So let's say that you bother playing the lottery if in expectation you expect to break even. So how big should the jackpot be for you to make it worthwhile? I should say to break even, not even make it worthwhile. So let's calculate it. We take the same formula as before, that expectation of x is probability of loss times minus 3 plus probability of win times the jackpot minus 3. And let's say breaking even is when you expect to win or lose $0. Solving this equation for the amount of jackpot, you'll see that it's 42 million that would make the jackpot should be 42 million, so that an average player would expect to break even. That's a pretty significant number, which looks bigger than the normal jackpot that you're going to see.